You tramped all the way from Minnesota. Why is that?
I wanted to catch a spark.
If you're traveling
I'm
I'd be surprised. That's a big school.
Good evening, everyone. Let's start by acknowledging that Carleton's campus is on the traditional unceded territories of the Algonquin Anishinaabe. Carleton Science, our whole community, recognizes our continued responsibilities as individuals and as representatives of an educational institution towards engaging in active reconciliation by developing pathways for Indigenous students into our programs and by finding ways to recognize and highlight the importance of Indigenous ways of knowing in our curriculum. Good evening, everyone. My name is Maria DeRosa. I'm the Dean of Science here at Carleton University, and it's my great pleasure to welcome you all to the 2024 Fields Carleton Distinguished Lecture. Over the past 2 decades, our partnership with the Fields Institute has enriched the experiences of both our faculty and our students, providing opportunities to engage with some of the most amazing talents in our mathematics sphere. It's a broad sphere. It's a broad sphere. I see, I'm not a mathematician. Through scientific conferences, workshops, and more. A standout feature, of course, of this collaboration is this lecture series. Each year since 2005, we've invited internationally renowned speakers recognized for their expertise in mathematics or a related field to present both a public lecture and a specialized academic talk. Recent speakers have included Dr. Leon Glass, the Isidore Rosenfeld Chair in Cardiology and Professor of Physiology at McGill University for his groundbreaking work in applying mathematics to biological systems. We've also had Dr. Charmaine Dean, Professor of Statistics and Actuarial Sciences from the University of Waterloo, who delivered a timely lecture on comparing COVID-19 mortality across Ontario's 3 epidemic waves. But this evening, I don't know about you, but this time of year, when they're announcing the Nobel Prizes, is like a highlight for me as a scientist. So this year in particular, we are truly, truly honored to have with us Dr. Donna Strickland, 2018 Nobel Prize laureate, to present our 2024 Fields Carleton Distinguished Lecture. To introduce her, please join me in welcoming Dr. Rowan Thompson, Professor of Physics and a Canada Research Chair here at Carleton University.
Bonjour, Kwe, hello.
I'm so glad to see you all today. It's my great honor to introduce our speaker, Dr. Donna Strickland, who's a professor in the Department of Physics and Astronomy at the University of Waterloo. I remember very well the day in 2018 when it was announced that Dr. Strickland was being awarded the Nobel Prize in Physics. It was a day much like today. I was up early this morning. I had an 8:30 lecture, and I see at least one of my students, two of my students in the audience. They had a midterm this morning, so thank you for coming. I was up early and I heard on the radio, Dr. Donna Strickland, University of Waterloo, where I did my PhD, is being awarded the Nobel Prize. This was amazing. And in the air, there was excitement. So, walking down the hallway of the physics building, heading to this lecture, isn't it a great day for physics in Canada? Was just everywhere. And in my classroom that morning, which is the same course I was teaching this morning, the grad students were really excited. A Canadian was being awarded the Nobel Prize in Physics. And not only that, it was for research she'd done as a grad student. And so they were going, oh my goodness, where is my research going to take me? Where could it lead? What could happen? What might happen because of it? And so there was this excitement that was in the air, and it's shared here today. So there's that great element of inspiration. And it's Dr. Strickland's groundbreaking work in developing chirped pulse amplification alongside her PhD supervisor, Dr. Gérard Mourou, that was recognized. And this research has laid the foundation for creating the most intense laser pulses ever developed. And it's led to innovations in medicine, in manufacturing, and industry, not to mention many in research. And in research, these are very varied contributions. So with my colleague, Professor Sangeeta Murukar here at Carleton, we're looking at the response of cells to radiation, which is relevant for radiation medicine, radiation protection, thanks to Dr. Strickland's developments. So Dr. Strickland's accolades include being named a Companion of the Order of Canada, the Sloan Research Fellowship, Premier's Excellence Award, and Cottrell Scholar Award. She served as president of the Optical Society and is a member of the Royal Society of Canada and a fellow of the Royal Society. So we're greatly honored to have you here with us, Dr. Strickland. Thank you for coming.
To go? Oh, now I am. Ooh. Well, thank you very much for the kind introduction. I'm kind of thinking that maybe you should have had Hinton if you'd known he was going to win, because I think he's got to be the first Turing winner who's also now a Nobel winner. Anyway, I'm here to tell you what I did all those years ago. And so since there's students here, hopefully you figure out during this talk, why was I the lucky one that got to do this graduate student project when I joined Gérard Mourou's group, because he had a group of great students already there and still, as they say, so close. So that's part of it. The other big part of this talk really is the importance of doing both fundamental and applied research. Not necessarily the same person, but I'm going to walk us through 150 years of science here. And along the way, you're going to see that it was fundamental science that led to the new technologies. And so the first new technology in my talk will be a laser. And when the laser came along, it changed the intensity so much of light that it changed how light and matter interacted. And it was this new interaction that came along, which is called nonlinear optics, that stopped us from going to even higher intensities. And so this is what Gérard and I had to figure out and work around. And then when we worked around it, the intensities again got so high that the way light and matter interact changed again. And that's what brought us to this new area of high intensity laser physics. Am I pushing buttons? How many buttons have I pushed now? Let me go back. I can go one. And it was this new intensity that's now got us so that we can machine glass. Okay? Before that, we could machine steel, but glass, the light goes right through. So there was not using light to machine glass. But once we had this new, what I call a laser hammer, we could machine glass. So this is what I'm going to walk us through. So we're going to go back 150 years, and I'm showing you the 3 different colors of light that we see with our eye. Light actually is defined as the part of the electromagnetic spectrum that we see with our eye. I will tell you, those of us who work in optics take everything from the far infrared to X-rays now, because we don't want to be limited. But anyway, we'll stick with light we can see. All right, so if you go back 150 years, scientists were still trying to figure out, is light a wave or is light a particle? We're still trying to figure it out, but now we think it could be both. But back then, with classical physics, you had to choose. It had to be a wave or it had to be a particle. And there was experimental reason to think both. But it was a theorist or a mathematician, since we're talking fields here, Maxwell, who actually took the physics laws from experiments, put them all together into these 4 beautiful equations that we use to this day and call them Maxwell's equations. He added one piece to it to make it mathematically sound, and used them to show that light just had to be a wave. And it was such a strong theory, everybody had to go along with it and go, you're right, you're really showing us light has to be a wave. Now, I am an experimentalist, so I will tell you as an experimentalist, a theorist can say something is true, but only an experimentalist can prove it. Okay, so the experimentalists started to think then, what would the definitive experiment be to show light is a wave? So if you've ever been to, I mean, you have so many rivers and canals here, but a lake is, you're kind of missing. But, you know, if you can go to the lake or an ocean and you walk, you will see the water waves coming in. And you know that if you walk along a stony beach and the waves are small little ripples, the stones don't move. But when the waves come crashing in, they can push those stones well up the beach. And that gives, it's the height of the wave that gives the energy to the stones. So the experimentalists said, okay, we're going to do an analogous experiment. We're going to shine light on material. And if it's a wave, the electrons are going to come off. And then we're going to turn up the power, and the electrons will come off even faster. Now, I don't know actually why they chose to use different colors of light, but they did. And when they used red light, and red light, just so you know, is the longest wavelength wave that we see with our eyes. And so the wavelength, I can't, let me see. No, it doesn't work on that one. Anyways, the difference between, that's why they wanted me to use their slide thing. Anyway, too bad. So what we call the wavelength, the distance between the 2 peaks, the longest wavelength that we see is red. Green, which is why I normally use a green pointer, so let me show it to you, okay, is the one that we see the best. And then the shortest wavelength we see is violet. It's not quite a factor of 2 shorter, so in musical parlance, we don't even see a factor of 2, okay? We don't even see 1 octave. And so, but there's roughly this factor of 2 between what we see the longest and the shortest. Now, when they shone red light on the material, no electrons came off. They turned up the power, no electrons came off. When they used green light, electrons came off at a very slow speed. And when they turned up the power, more electrons came off, but still at that same slow speed. But when they used violet light, then the electrons came off at higher speed, and when they turned up the power, more electrons came off. But the speed seemed to be going with the distance between the crests, not the height of the wave. So there we were at the beginning of the 20th century, scientists scratching their heads again, saying, what does this mean? Because this means light really can't be a wave. So along comes this man, Max Planck. And Max Planck is the one, at the turn of the century, that showed us that you simply cannot turn the power of light all the way down to 0 continuously. There is this minimum energy unit, and that minimum energy unit is what we now call the photon. And he also showed us that a photon's energy is indeed given, of a single photon, is given by the inverse of the distance between the waves. So this is how rapidly do the peaks hit you. All right, so now again, in our heart and soul, just like we all can see, imagine that the height of the wave should be where the power is, we all feel gravity in our everyday life. We know if we want to sled down, this is a Canadian audience, I love it. Snow comes in a lot in my thing. So if we want to sled down a hill, we know we want to go to a big hill so that we can go fast down the hill. We know that if we want to pick up something heavy, it takes a lot more energy to lift it way up versus just slightly, okay? So we're going to use height then as our depictor of energy. And so the red photons, which have the least energy, I consider child-sized photons. and they can only pick up the electron that high. The green photons are then like adult-sized photons, and the violet photons, being almost twice as high, are like basketball-playing adults, okay? Now, why are we going to talk about basketball? We're going to have them play basketball. So Albert Einstein, who could have won his Nobel Prize for so many things, he didn't win it for what you think. He didn't win it for E equals mc squared. He didn't win it for general or special relativity. He won it for this photonics or optics thing, all right? So he's the one who explained it, but using Planck's idea of photons' energy. So now we're going to think about playing basketball with our photons and with a child-sized basketball net. So now if you're a child playing basketball with a child-sized net and you want to dunk the ball, even on your tippy toes, you can't do it. If you turn up the power in the photon picture, what you're doing is increasing the number of photons, and actually it's the density of photons. So it would be like having a whole lot of child-sized photons all around that net, but none of them can dunk that ball. But now with your adult size, which is the only reason I ever play basketball, if I'm going to play it, it's going to be with a child-sized net. And that's because I can dunk in a child-sized net. And so, but I'm just barely taller, and so the ball just barely, picks up speed before it goes through the net. Again, if I turn up the power of green photons, there would be all these green photons dunking the balls, and they would all be going through at that same slow speed. And finally, with our ultraviolet would be twice, violet photons, those pro basketball playing people, their balls are going through fast. So this is what Einstein explained to us. Usually when we talk about the photoelectric effect in our undergraduate classes, we're talking about the quantum mechanics of it. But for this talk, I'm not so worried about the quantum mechanics of it. This is an example of a linear interaction. And what I mean by a linear interaction is that it's always one photon interacting with one atom at a time. And if that photon energy has more energy than what the atom is holding onto its electron with, then the electron can leave with the difference in energy, because energy is always conserved, okay? Now, if you have a whole lot more photons at play, they can meet up with a whole lot more atoms, and that's why more electrons go off. But the interaction is always one photon with one atom at a time. But if you double the number of photons, you'll double the number of electrons. If you triple the number of photons, you'll triple the number of electrons, and that's why it's considered a linear process, okay? So now we are there at the beginning of the 20th century, and we probably think we've got it all figured out. But no. Along comes this woman, Maria Goeppert-Mayer. Now, she is famous for being the second woman, after Marie Curie, to win the Nobel Prize in physics. But that's for work she did in the 1950s on nuclear shell model, which has nothing to do with this talk, so we don't need to discuss it. But when she was still a graduate student, back in Germany, working with Max Born, she's the one who asked the question, why are atoms stuck only dealing with photons one at a time? Why can't atoms, absorb the energy of two photons at the same time? And she's a theorist, so she doesn't have to worry about technology. She can just think with her head and write down math with her, pen and paper. I usually don't say math, but now that it's a fields lecture, she showed us the calculation, and sure enough, now she did it for two photon absorption, but sticking with the idea of the electron coming off, which we call ionization, it would then come off with twice. And remember, violet isn't quite twice, but you can't really show you ultraviolet, so we're sticking with violet. And so it would give you the same energy as equal to 2 red photons. That's what the interaction would be. So she showed us, she did this work in 1930. She published the paper, and again, for all grad students here, sole author publication. And she's the one who showed us. She could have started a whole new field of physics called multiphoton physics. Could have won a Nobel Prize for that, but no. Anyway, that's okay. She won it later on. She's the one who showed us it would work. Nobody saw it. So she published the paper in 1931. Nobody saw it until 1961. Now, you'll also see that I now call this nonlinear optics, whereas before I called it multiphoton physics. I will tell you, I'm such a slow learner. that I didn't know for 30 years that there was a difference between nonlinear optics and multiphoton physics. So I'm going to straighten that up for you guys right away. So the difference is, if you're a molecular and atomic physicist, and you're watching what happens to the atom or the molecule, you are doing multiphoton physics. But if you are watching what happens to the light, then you're doing nonlinear optics. It was a very subtle difference, but the first experiment really was a nonlinear optics experiment. It was done by the University of Michigan and Peter Franken. Do I have, oh, yeah, in the talk I'm giving apparently tomorrow, I will have the authors of the work. And I will tell you also, just in case there's undergraduates here, this work was done by an undergrad doing their 4th-year research project. Yes, indeed. OK, so this experiment was not about 2-photon absorption, where the atom would just absorb the energy and hang on to it. It wasn't 2-photon ionization, which is what I've talked about, the electron coming off. No. This experiment was the atoms would absorb, each atom would absorb 2 red photons, but then let that energy go, but not as 2 red photons, but as 1 photon with twice the energy. Again, that would be in the ultraviolet, but I can't draw that, so we'll draw it as violet. Okay? And so this is what we now call second harmonic generation. So that was done in 1961. So the question is, Maria Goffman told us in 1931 it should happen. Why did it take 30 years for us to see it? Well, I already told you in the preamble, we needed the technology. So this is my Nobel talk, so I do pay homage to all of the people who won Nobel Prizes ahead of me in this field. Basov and Prokhorov were working together in Russia. They were working independently from Charles Towns, who was in the United States. These are the 3 gentlemen that are given credit for developing the maser. The maser is like a laser, but the M stands for microwave, and the L stands for light. So a microwave photon is even lower, much, much lower energy than a red photon. And the lower the energy, the easier the lasering process is. I'm not going to explain that here. This is why we're still waiting to get a real X-ray laser. We're still working on that. All right, so they're the ones. Now, Art Shallow won a Nobel Prize a few years later for laser spectroscopy. I'd like to point out that he's almost Canadian, in that his mother was Canadian, and he did all his degrees at the University of Toronto, so close enough. But he was down in the United States when he did his Nobel Prize winning work, but OK. But those are the 4 that won the Nobel Prize for lasers, but it's really this guy, and unfortunately, for whatever reason, he did not get to win the Nobel Prize. But Ted Maiman was the one who was the first one to figure out how to take that maser technology and get it to work up at the optical frequencies. And so he was working at Hughes Aircraft at the time, and he first demonstrated a laser on May 16th, 1960. OK, so what is so special about laser light? So I have very strong lights shining on me here, and there's lights on the room. And we use these lights because you will see it's white light. If we see white, it means that we're seeing every color we can in our eyes. And so every color that we see is coming out of these lights. It's also lighting us all up because regular light lets the photons go in every single direction that there is, and so that works well for lighting us up. Most importantly, though, for regular light, the photons coming from the light bulb don't care of what the other photons are doing. Every photon just says, I'm going to go in this direction at this color, when I feel like going, OK? But when you have a laser, and this is a laser pointer that I'm using, so let me shine it here so you can see it. There we go. You will see it's quite bright. Even though there's really bright lights on me, you can see this, and it's only 1 milliwatt, hopefully, because otherwise it wouldn't be eye safe. You wouldn't want me slinging it around. It's only 1 milliwatt of power, and this will be hundreds of watts coming at me. But you can see it looks bright, and that's because it's only 1 color. All of the light is going in 1 direction, which is why it's a tiny little dot. All the light coming out of here is not going everywhere. They're all going together, as shown in that picture. Only those are red photons. But most importantly, all the photons coming out of a laser know what each other are doing. So if one's peaking, they're all peaking, and so if one's troughing, they're all troughing. And this way, when they add up, this is how they add up to be a great big giant wave. But I like to think about linear and nonlinear optics in my photon picture. So now, this is regular light again. and all different colors are coming out. And so I like to say all the photons are dancing to their own beat. And not only are they all dancing to their own beat, they don't care how anybody else is dancing, and so they cannot crowd onto the dance floor. Now we can try to force these photons together by using a lens, and that would take the beam of light and focus it down tight. And if you try to do that, it'll look very tight, but it cannot go smaller than the wavelength. And the wavelengths that we see are a fraction of a micron, about a half a micron. Green light is half a micron. Your hair is about 50 microns. So it's about 100 times smaller. You can focus 100 times smaller than your hair. And that seems pretty small, because your hair seems pretty small. But compared to the size of an atom, a single atom, that's 10,000. The diameter of an atom is 10,000 times smaller than that. So if you think about trying to absorb the energy of two photons at the same time, the two photons have to be in that interaction volume at the same time. And the density of photons coming out, even of these lights that seem quite bright, are too small to be in the volume at the same time. So it didn't work with regular light, but when the laser came along, now Nicholas Bloomberg won the Nobel Prize with Art Shallow, but I've put him on this one because he is considered to be the father of nonlinear optics, like Maria Goldberg is the mother of multiphoton physics. So I've left him on this one. When the laser came along, now they were all dancing to the same beat, and they were all dancing together to the same beat. And because they were dancing all together to the same beat, now they could crowd onto the dance floor. And so in 1961, with one of the original Ruby lasers, the Michigan group could focus it down, and there was that chance in 1 million to 10 million that they had two photons in the volume of the atom at the same time, and had that chance in 1 million to 10 million of observing two photons being turned into blue light. All righty, so the laser brought us to here. Now, what's this got to do with me? When I joined Gérard Mourou's group, I was the 7th student in the group, okay, but everybody else in Gérard's group was trying to make their lasers shorter so they could measure something faster. When I joined the group, Gérard gave me this paper written in 1973, and I joined the group in 81. So I don't know why he was reading this 8-year-old paper, but he was. And he said, and probably because now we had lasers that he thought almost might work. In 73, we probably did not. But Stephen Harris, a professor, still a professor at Stanford, probably emeritus by now, he was sort of the one thinking, it's great that we have laser light in the infrared and into the red, but wouldn't it be great if we could get that coherent radiation, that's what we call it when all the photons are talking to each other, wouldn't that be great if we could get that out into the ultraviolet, vacuum ultraviolet, maybe even further out? And so he came up with some schemes as to how to do it. So Gérard gave me this paper, and he said, you know, if this is what you want to do, then figure out how we can do it, and with one of the lasers that we have in the group. So I thought about it, and I came up with a scheme that I would look for the 9th harmonic, 9 photons being absorbed at the same time, and creating one photon with 9 times the energy in twice ionized nickel. So my PhD, so this is what I'm, here, let me just show you. This was what I was aiming for. Here we go. My PhD had 2 parts. The first part was to figure out how to make a cold plasma of twice ionized nickel. Never figured that part out, so we won't discuss it anymore, except to say that this just 2 days ago, I was in Montreal listening to some high-intensity laser people, and they are seeing this, and they said, this is not following what high harmonic generation is. This is, and I went, you should read the paper from 1973, Stephen Harris, because I couldn't figure it out 40 years ago, but you seem to have figured it out. So maybe we're doing it finally. Anyway, it didn't work. But I didn't need just 2 photons or even 3 photons in my interaction volume. I was going to need 9 photons in my interaction volume. So I couldn't just use a laser. I had to have an intense laser. That part of my project obviously worked, which is why I'm here talking to you tonight. So that's what we're going to talk about. So how did I do it? What's the difference between a laser and an intense laser? So I've talked about its, photon density. So one of the things that still amazes me to this day is how fast light travels. So now I can take my laser pulse here. Where should I show it? There we go. Can we all see that? And I can turn it into a 1 second light pulse just by letting it go. Now let's say this was a glass ceiling, not the proverbial kind. And I sent it, and the moon was up there. I have no idea where the moon is because I'm not an astral person. But you know, let's say that looks like a window. I could send it out and see if the moon's there. Hope I didn't blind anyone. Anyway, in 1 second, the light will have gotten almost 3/4 of the way to the moon. Now, usually I talk about how many hours it took me to fly wherever I am. But even so, it's going to take me over an hour to fly back to Toronto tomorrow, and yet light can get 3/4 of the way to the moon in 1 second. It's very, very quick. So a 1 second light pulse, if it's not stopped by like a ceiling, will stretch out over 300,000 kilometers. It's a one long line of light. Okay? Now you'll see that I've got an energy there of 1 millijoule. So there's 2 reasons for that. One is that the paper that I wrote that got me the Nobel Prize was about a laser that made 1 millijoule of energy. 2, that's what's coming out of this laser pointer every second, because it's 1 milliwatt to keep it eye safe, and power is energy per unit time. So every second coming out of this laser pointer is 1 millijoule of energy. Now, if I hold it really steady, I can almost feel my hand warm up there, but not really. So you think, what's the big whoop-de-doo about 1 millijoule of energy? But I can tell you, to cut the glass in your cell phone or to cut the cornea of your eye, you don't need any more than 1 millijoule of energy. So what's the difference between the millijoule coming out of here and the millijoule that cuts glass or your cornea or anything else clear? Is the density of the photons. All right? So 1 second stretches out over 300,000 kilometers. That first nonlinear optics experiment that saw 2 photons being absorbed in one shot in 1 million to 10 million was a millisecond. That's still 300 kilometers long. I will also say it was a joule, not a millijoule. So it's 1 million times stronger than what's coming out of here. But that wasn't enough, because I needed 9 photons. And so we brought it down to 1 picosecond, which is 1/millionth of a second, or 1/3 of a millimeter. So all of the energy that comes out of here, stretched across 300,000 kilometers, was squeezed down into being just 1/3 of a millimeter. Okay? And that's how we got the photon density way, way up. So how did we do it? So I'm going to take us back to Earth, and we're going to go to Rochester, New York, and the Laboratory for Laser Energetics, which is where I did the research, and that's a young me, if you can see me. And my dad took the picture. That's his car. It is a DOE-funded facility, Department of Energy-funded facility for laser fusion. All right, so it was actually a fellow Canadian that saw me. I was wearing my iron ring, saying I graduated from an engineering school. All my degrees are in engineering, and yet I'm a physics prof. Who knew? Anyway, he comes barreling in, and he said, oh, and he saw the ring. He goes, I was told there was another Canadian here. And he sits down beside me, and he asks me what I want to do. And I said, I want to study lasers. And he went, then I know the guy for you. And so he took me the next day. So the very first week I was in Rochester, I went over to the Laboratory for Laser Energetics. He walked me into this lab. We were not as laser safe in those days, so I could see the beautiful green and red beams with my eyes. And I just thought, how much fun would this be? It would be like working around a Christmas tree all year long. So I met Gérard, and I started working with him a month later. So this is an example. This laser was already going when I joined the group. The red beam is the actual dye laser beam. The green is pumping that one. You'll see there's an orange hose there coming along. I mean, it is a dye. So if that orange liquid got on your clothes, you had dyed your clothes orange. All right? And so this is an example of an ultra-short pulse laser. This was already 10 times shorter than what I'm talking about. So all of the photons were coming in just 1/30th of a millimeter. Okay? And so the slugs of light would be almost looking like, if you remember, people hardly use paper anymore, but if you still use paper and do a 3-hole punch and you get those little pieces of paper, that's really what the light pulses would look like going around this lab if you could really see them. Okay? So we had short pulses. But as I'll explain later, a dye laser cannot be made energetic. So we had short pulses if you wanted to measure something fast. Now right across the lobby, though, was this laser. This is the laser that's used for laser fusion. Laser fusion is an application that requires energy in to get energy out. And just 2 years ago, we finally got scientific break-even of laser fusion, but at Lawrence Livermore National Laboratory uses a megajoule of energy, and they then got more than that. They used 3 megajoules and got more than 3 megajoules out. Okay, this laser, just so you have an idea of the scale, the whole footprint of this laser is like a football field. And these green sort of things that are sticking up there, that's the size of a human adult, okay? So this laser is a big laser, and this is a kilojoule, so you can imagine how big the National Ignition Facility is for their megajoule laser, all right? And I'm going to explain again later in my talk why it has to be so big to be energetic. But it can be energetic, and it can be big. And so we had big energy lasers, and we had short pulse lasers. When they put short pulses through this laser, or one arm of this laser, it destroyed the laser. So that made 2 things happen. People who studied nonlinear optics, because no one was expecting that, or they wouldn't have put down a very expensive laser, went off to study why did it do that. But laser jocks like me got told, do not put short pulses down our very expensive lasers because it causes too much damage that costs too much money. Okay? So that's where we were when I joined the group in the 80s. We had short pulses, big energy. You did not put them together. So that's why we had to come up with chirped pulse amplification. So I like to say that I have like the simplest Nobel Prize to explain. You'll also see this will be the first Nobel picture that's in color. That's because I prepared this talk the year I won, and so I said I'm present day and the rest are history, but of course I'm now history too. So I could go to black and white, but I won't. All right, so I'm going to go down here because I am going to, you guys are all going to have to watch way down here, but I'm going down here because my point is not working. You guys can see this, and I'll do something for them down there. Okay. I want a laser hammer. This is my laser hammer. I want a lot of energy. I want a really short pulse. I do not want my laser hammer hammering my laser amplifier. This was the problem. So, very simple idea. We have short pulse lasers, like the dye laser I showed you. You can have short pulses. We're simply going to stretch the pulses to be long, density of photons low. The amplifier, makes a lot more photons, but you make sure that you've got them stretched far enough so the density does not get high here. And then when you're safely outside, you can press it back so that you have your laser hammer out here. So my first laser was a millijoule. My first successful laser, I should say, I do want to point this out to students because people make a big deal about it being my very first paper, but I was in my 4th year of grad school. That's how many failures I'd had before this success. Anyway, so we could have called it stretched pulse amplification, but that's kind of boring. So we called it chirped pulse amplification because we do use the fact that we use what's known as dispersion to make the red come out ahead of the blue. Okay? And a bird's chirp is the fact that the audio frequency changes in time. And so this is the same idea. The color or the optical frequency is changing in time through the pulse. And so that's called an optical chirp. And so we call chirped pulse amplification. I'll also say that because it was just a millijoule of energy, we could compress in air. But the most intense lasers now, and the one I was just visiting in Montreal, the compressor must sit in a vacuum because even air becomes a nonlinear medium and you actually hammer the air and things happen in air once you're past a joule. All right, so now let's explain how we did it. So now this looks like, I'm showing you the very same lasers I showed you before, because I am. But I'm going to come down to your side now, and I'll cause some screaming as I go by. Okay, so the dye laser. This is the dye, and this is the red beam coming from the dye. And it is pumped by this green laser. Green photons, more energy than the red photons. So this is why you have to have more energy to pump. Okay, I will also tell you that our laser mirrors are really good. 99.99, possibly 9% of that green is turning this corner. This is you'll see it used to be called dye laser, now it's called neodymium YAG laser, and that's this orange box and these two mirrors here. This laser lasers in the infrared 1 micron. We cannot see that color. The camera cannot see that color, but 2 watts, not a milliwatt like this guy, 2,000 times like this, coming out infrared. It goes into this thing here, and this is a frequency doubler. The same thing that the Michigan group saw in one shot in 1 million to 10 million that they could see frequency doubling. We now have enough intensity here that this is now working 10%. So 2 watts became 200 milliwatts of green, but that meant most of the 2 watts goes to this mirror that doesn't work at all for 1 micron. So it comes on through and just goes into a beam dump. So there was no money for this project, and so I had to use the leftover light, okay? And I already thought, like when I said I was going to do the 9th harmonic, it was the 9th harmonic of the wavelength of neodymium YAG. I knew that was one of the lasers that was at my disposal. All right, so you'll see that it's very crowded there for me. But there I am, 1984, a whole very young thing. And this is for the cover of the LLE Quarterly Review. They always put students on the cover to show how they were educating people at this DOE facility. So let me just explain a few things that show up in this picture. One, you'll see that we had to show we were eye safe. And so that was our 1980s laser goggles. Aren't they lovely? It was a professional photographer that came in to do these pictures. He did not like the green glass covering my eyes. So I'm actually only wearing frames, okay? But it's okay because the YAG laser's infrared, so you can't tell if it's on or off. So it's off, and I'm safe, but I'm just wearing frames. Now, the photographer also wanted me to be tweaking something. He actually wanted me to touch a knob. I went, no, you're crazy, no. I've been working all year lining this up, no. So I'm holding nothing there, but you can't tell. Now, the big spool of fiber is holding my 1.4 kilometers of fiber, and this is going to be my pulse stretcher. So I never used to say why it was 1.4 kilometers. And then early on, I gave a talk at the University of Toronto, and one young woman asked me why 1.4 kilometers. And I could tell she was very disappointed in my answer. I could tell that she was thinking, you won a Nobel Prize for this. You should have had to do some really difficult calculation for this Nobel Prize winning project. But I did not. So how come 1.4 kilometers? Well, I already told you there was no money for this, but once we decided to do it, you'll have to come to tomorrow's talk to find out why we decided right then it had to be then and now. There was no time to apply for grants and get money and do all of this. No. We're going to use the YAG that's already there. Gérard knew that he had done his PhD back in France with a neodymium glass laser, which is what we're going to use to amplify. He calls up to his old group back in France, or maybe Quebec, because they moved partway through, but I think it came from France. Do you still have that old laser of mine? Yes. Can you ship it to me? So I had his hand-me-down amplifier. Then he called Corning, which is just an hour south of Rochester. It's a great glass company, makes Christmas ornaments, but it also makes optical fiber for communications. And they had just come out with a new fiber for this wavelength, this neodymium YAG wavelength. So it was a specialty fiber. Now, another word for specialty fiber is very expensive fiber. So Gérard called and said, this is going to be a very important experiment. Don't you want to be part of this very important experiment? Don't you want to donate fiber? And Corning very generously donated 2.5 kilometers of optical fiber on that spool. Now, I guess most people that want 2.5 kilometers of fiber want to lay it across 2.5 kilometers. So that came with only one end showing. But I needed the light in and I needed the light out. So I needed to get to the other end. So I had to spend a day of my life unspooling and respooling. But I was the first person at the Laboratory for Laser Energetics to ever have a spool of fiber. And so there was no more spools. So, and you have to be old to even know what I'm talking about here, so I'm sorry for all you young people. But for those of you who have gray hair like me, it was an old film canister that I glued corks around, and I spent a day doing this, 2.5 kilometers. Then I tried to put the light through, and the light did not come out. So I had to pick up my IR viewer to see where that light was coming. And as Murphy's Law goes, it was broken, but luckily only once, but of course almost in the middle. So again, I had to re-spool to figure out which was the longer. And 1.4 kilometers was the longer half. And that's why we use 1.4 kilometers of optical fiber. 2.5 kilometers isn't even long enough, but that's okay. It was long enough to do the experiment. So again, students, if things go wrong, just keep going forward. Okay, that's the long story. So the only thing, the Laboratory for Laser Energetics themselves bought the gratings, which you'll see that we use at the end. Okay, that was the only thing that was purchased to do this project. Don't want to say anything else about that lovely picture? I don't think so. All right, so how do we do it? So when I first introduced lasers, I said everything is one color. If it is one color, then it has to go on forever and ever and ever as that one color. And so actually short pulse lasers have a lot of colors, just like this light bulb. But also, we have something in our laser called a mode locker, and I like to think of the mode locker as like a symphony orchestra conductor. So now, if you go and listen to a symphony orchestra play, and they're just warming up in front of you, they sound terrible, because they're all tuning up their own instruments, playing their own notes, and so it just sounds like noise, and that's the same. That's the audio version of what comes out of a lamp, okay? It's every note being played at its own time when it feels like it. But when that conductor brings down his baton, they all play their different notes together, and it's beautiful music. And so that's what we have in our mode-locked lasers. We have something that says to all of the colors, at this point in time, go now. So every color you'll see in the middle of my picture there is peaking, okay? But because each color has a different distance to the next peak and then the next peak, as you go away from that one place, you will see as you go, there's just as many peaks as there is troughs. And so when you add all the colors, the black one is the addition of all the colors together. And the broader, the more colors you bring in, the faster it goes to zero. So the more colors you have, the shorter pulse you can have. So we need a lot of colors. So we have the colors, we put them all together. I'll also say the black is then the shortest it can be, okay? And so it looks like, if you look at the black, it looks like it's a single color, and it'll be sort of the middle of all of those colors, okay? But they go to zero, so it says all those colors have to be there. All right, once you have all the colors, now this is why I used a fiber. So in empty space or vacuum, all colors travel at the same speed. But remember that I talked about how the atoms are holding on to these electrons with certain energies. So something that's transparent means that for the colors we see, there are no quantum levels there. They're either way down low for the colors that we're using, or they're way up high. And we're going to talk about the ones way up high. And this is why glass is clear. It's up here in the ultraviolet. So now the red photon comes along and goes, we've got nothing in common. I don't even need to talk to you. And the green comes along and wonders a little bit. And the blue, they almost think they could be friends, but not quite. And so this is why the red photons pretty much run right through the fiber. The green walks, and the blue crawls along. And so after my 1.4 kilometers of fiber, I had to stretch pulse. It was stretched at this point to 1/3 of a nanosecond. A nanosecond is 10 to the minus 9 seconds. Now, for the old ones amongst us, we're going to know what this means, because we'll remember the American units. But we've gone SI up here in Canada, but this works better when I'm talking in the States. A nanosecond pulse is a foot long, okay? So, and you'll see that what I really wanted was a foot long, and I only, with my 1.4 kilometers, only got 1/3 of that. But even 2.5 kilometers, I wouldn't have quite got there anyway. So I'll explain what the problem is. I couldn't turn up the energy quite as much as I should have. All right, so now we've got the pulse stretched, we're ready to go into amplifier. So this is a laser amplifier. So I also like to joke with my atomic and molecular colleagues that I am an optical physicist. So in my slides, only photons have personality. So these are atoms. So these atoms are sitting there in their ground state, and they're waiting to be excited. And so we'll pump them up. For the glass laser that I use, neodymium glass, it is pumped with ultraviolet lamps all around them. If you engineer it right, you'll just have a few that don't get excited. They shouldn't all be on the edge. I don't know why my communications team thought the ones not light up would all be on the edge, but there you go. There would be a few that didn't get there. Now, I told you the dye laser can't be made energetic the glass can be made energetic, but it has to be big. So why is that? A dye laser is like a sprinter, and a glass laser is like a marathoner. They both put out a lot of energy to win the race, but they do it differently. All right, so the dye laser gets excited up and then goes, I want to let this go. I don't want to hang on to this energy. I want to let go right away. So what happens is that any one of those atoms can let go its energy and go back to a gray state, and the photon goes in some direction. If it hits another one of these, that's called stimulated emission, and it will cause it to go, and it'll cause light to go this way, up. So if you try to make it very big, you just end up with a giant light bulb. This is why that kind of laser can't be made big and energetic. On the other hand, neodymium glass has got to be one of the largest stored energy systems, and it sits there and goes, I'm a marathoner. You pump me up. I'm going to wait until a photon comes along to take the energy. So here comes the photon. You'll see the photon is the very same color as what the atom's pumped up to. So a lot of people don't know this, but actually the equations that gives us the laser also came from Einstein. The man did pretty much everything. So he's the one who's told us that, I mean, absorption was already known, that if your quantum level's here and there's a quantum level there, and you use exactly that amount of photon energy, then you can pump it up. But he showed stimulated emission's the same thing in reverse. If it's up in this level and you go into exactly that photon energy, it will kick it down to the ground state, and the photon will go with the other photon, and they will just walk hand in hand together. So there you go. So those two photons then find two more atoms, and they take the energy, and they walk 4 photons hand in hand, and those 4 become 8. There you go. All lasers start this way. It all starts with one noise photon going in the right direction. Okay. Every type of laser material has what's known as a saturation energy flux. So the dye one is very small. The glass is one of the largest at 5 joules per square centimeter. So lasers start with focusing mirrors, and you focus down very tight, because if you're going to efficiently extract that energy, you need to get up to that level. So for glass, you need to get up to that 5 joules per square centimeter, and then, here comes another snow analogy. I know we're not quite ready to get there yet, but you want to be like a snowplow to take out all of that photons. So you have to get up to that. So we focus down tight, because we have to start with that single photon. But then it gets up to that 5 joules per square centimeter, but it's just a very, very tiny spot. You blow up the spot, you go through an amplifier, you get it up to that 5 joules per square centimeter, you make the spot bigger, you make the spot bigger, you make the spot bigger, and you keep going through the next amplifier. And that's how you can, if the energy source is willing to sit around and wait for those photons to come, you can keep making your system bigger and sending the beams through and getting a lot of energy. So now, to make sure that you don't have a laser hammer inside your laser, though, that's the photon density. So once you know what photons per area you're going to use in order to be the snowplow to efficiently take it, that tells you how long you have to be so that the density of photons at 5 joules per square centimeter stays below whatever the nonlinearity of the material is. And that's why we knew already, because people already looked at this, that we needed to have this foot-long or nanosecond-long pulse, which we didn't quite have. And so I did damage a couple of rods. I tried to get a colleague who's still there to look for a damaged rod, because I have to put something into the Nobel Museum in Stockholm, but they found a pristine rod that came from my laser, and it had my hand printing on the lamp box, but anyway. And they also had lost the fiber. I kind of tried to convince Corning just to make another spool look the same, because nobody would know, but no. I didn't get to cheat. All right, so once we have it amplified, now it's time to compress, and we used a pair of gratings. So we've all seen light go through prisms, and the different colors bend different amounts going through a glass prism. Gratings just do it more, okay? So gratings are these things that are ruled, but you'll see the red is out ahead of the green, ahead of the blue. And so if you watch how the red will bend more than the green, more than the blue. Use 2 parallel gratings so that all the beams come off parallel. But if you put the gratings just the right distance apart for however long you've stretched it, you have all of the paths back together, and you have a short pulse at the end of your gratings, and that's the whole story. So it was a Thursday night, I still remember it, back in 1985, when I had finished the project, but I had no way to measure that it worked. I had set it up with the oscillator pulses that are coming out every 10 nanoseconds. We had a way to measure how short those pulses were. So I did set up the stretcher and the compressor and make sure they would compress. But the amplifier only worked at 10 hertz, and so I had no way to measure it. Luckily, my friend and colleague, Steve Williamson, had just bought a new type of streak camera, which was something that could do it. He said, I think my streak camera can work. And so he came in that Thursday night and worked with me. And we used an Etalon and to do it all, and showed that it was camera limited at 2 picoseconds, which is sort of, I had compressed them to 1.5 pico, so that was close enough to working. So that was it. I will also say that I put Steve Williamson's name on the paper. So there could have been 3 authors, and I may not have gotten the Nobel Prize, or he maybe would have gotten the Nobel Prize. It was a lesson in really graciousness that I learned early on. He said, Donna, you've worked so hard on this project. Don't let anybody else take credit away from you. I don't need to be on the paper. And he took his name off the paper. And so that's why there was just the 2 of us on the paper. Anyway, that was it. All right, so now back to the fact that not only could I not figure out how to make a cold plasma of twice ionized nickel, by the time I got that laser to work, and then we had the 2 more amplifiers, so we had enough energy, the joule, to do the nonlinear optics experiment I wanted to do, the French group had already seen the 33rd harmonic, which is why Anne Lullier just won the Nobel Prize a year ago for that work. But it was sort of like blew my whole 9th harmonic, even if I could have figured out how to do it, sort of out of the, it was like, why even bother? So we had to do something else. And luckily for me, Silong Chin from University of Laval in Quebec City wanted to be one of the first people to use this new CPA laser. So he came down to do a sabbatical, and he helped convince Gérard that I should just study multiphoton ionization, which is another reason why I started with the photoelectric effect. We'll just do the multiphoton version of that, because I had the world's most intense laser, short pulse laser, and I could show this working better than anybody else. So if it had been nonlinear optics or multiphoton physics, in this case we're watching the ion, so it is multiphoton physics, it was going to take, we're using noble gases, it was going to take 11 photons to kick the electron up and shoot it out, okay? That's a different, I don't use basketball. Now, we all picture the electrons being held in these wells, and so that's what it takes to kick it out. If this was what was working, and this is how we understand 2nd harmonic and 3rd harmonic and what Maria Groper-Mayer talked about, it would have gone to the 11th order in power. It did not. We were now where the intensity was so high, we could forget about the photon picture altogether. We were back to just classical wave physics, and we just had one great big giant wave. And that big giant wave could just tip the well over, and the electron's free to leave. And so now we've made the light so intense that it once again changed how light and matter interact. And it's using this process that we cut glass and we machine the cornea, which I'm going to show you at the end of this talk. All right, so this is a slide that Gérard's been showing for many years. It used to be vertical. And it shows intensity over the years. And it starts in 1960 because that's when the laser was invented. Obviously, many, many orders of magnitude were improved then. Q switching and mode locking are ways to make the pulses shorter. Then you'll see we had this plateau because we couldn't amplify it. CPA came along in 1985. When we did this work, Gérard, my very first time even speaking at a post-deadline paper about it, Gérard said, you've got to say this is how we're going to make a petawatt laser. Because we had kilojoule lasers, and we showed we could do a picosecond. And it was the very same kind of laser, so it should have worked. Okay? But people didn't want to do it, because the way we did it originally was with that fiber. Again, the fiber's got a 9-micron core, so anything sags and moves and the power doesn't go into the fiber, it wouldn't have done the stretching like we thought. And if it didn't do the stretching like we thought, we wouldn't have a long pulse going into our very expensive one, and so people did not want to risk this. Okay, so now we don't do it that way. And sometimes students who work with this kind of laser go, but I don't understand, why did you use a fiber? We use gratings. I went, that's because the grating stretcher wasn't invented until 1987, and I was doing this work in 1984. Okay, so now we got around that. So the French decided they were going to do it, and Gérard pushed for the French to do it. But then Livermore said there was a good science reason to do it, but I kind of think, you just don't want the French to beat you. I don't say that when I'm in the States. Okay, don't repeat what I said. But Livermore started to do it in 1991. It actually took 5 years. Once they decided to do it, it took 5 years. And the reason is that the glass has 5 joules per square centimeter, but the gratings I used only could stand 50 millijoules per square centimeter. These gratings are rules, 1,800 lines per millimeter, and they have to be perfect or it's not going to do the compression like you think. And so they had to not only figure out how to get that up, and over the 5 years, they instituted a whole grading program. They didn't do gratings before this. They got it themselves, and they got it up to 1 joule per square centimeter, and they figured out how to make that ruling perfect over a 1 meter size. And so they had to work on both of those things in order to make it happen. So they were the first to hit a petawatt. Gérard's is there. Gérard's is the QOS one. It's more intense, but that's because the one at Livermore was being used for fusion, and it wasn't being focused to a tight spot. He focused it to a tight spot. And he had to use deformable mirrors like they do in astrophysics to undo all of the phase problems. And he got down to single micron size. So he had, for a while, the most intense laser pulses. I've added the last 2 dots, and I don't know how to change the line, but the blue one is the most powerful laser in the world. It's not the most intense, but it is the most powerful at 10 petawatts, and it sits in Europe. The black one is the highest measured intensity, and both of those happened during COVID. It's a 4 petawatt laser. It's focused to single wavelength dimensions, and so it's at 10 to the 23 watts per square centimeter. Now, if I did know how to take Gérard's slide and roll it over, you would see that we have, again, rolled over. So again, I like to point out to all the young people, it is time for a new Nobel Prize winning idea to kick us on up again, because we'd like to get up to that orange block. That orange block is where we will break the vacuum with light. So our high energy physics friends tell us that vacuum is not nothing. Our quantum people would tell us we have quantum fluctuations, but let's forget that. The high energy people would say that we have matter with antimatter, okay? Also could be called quantum fluctuations. And so now you could have an electron connected to a positron. The rest mass of the electron and the rest mass of the positron, same. And E equals mc squared, one of the many things that Einstein did for us. So that gives us the total energy of that particle. We know the distance between that particle, okay, Compton wavelength. And so the force is the energy divided by that wavelength, or distance, and that's the force. That electric force between those 2 charges is the same as the electric force of the laser field if we get it to 10 to the 29 watts per square centimeter. So maybe we could focus in a vacuum and watch mass come out. It'd be fun to see. I hope to see it in my lifetime. I'm not going to work on it, but I want to see somebody do it before I'm dead. So that's what we're all aiming for. But of course, there's plenty of things to do in those other boxes too. So so I'm just going to finish now with the eye machining. When I get to that video, if you're squeamish, you won't want to watch it. But there are great videos out there of just kilowatt lasers machining steel. Okay? And they can go through inch-thick steel and quite quickly. But that's the same linear optical process of us standing out in the sun, and the sun, us causing a shadow, the light goes in, it gets stopped by us, and that light energy turns into heat. So when you do it with a tiny laser beam, all of that heat is in a small area, and it's so much it can just melt and evaporate the steel away. And so that's how you machine steel, but you also then have to machine from the edge in because it's being absorbed. But that's not true of glass, right? Like I take my glasses off and the beam goes right on through. So it's not going to be converted into heat. But now we have a laser hammer. So here it is. So we're going to show you, I'm going to show you cutting the flap of the cornea. The reason that we cut a flap is that if you've ever poked yourself in the eye, and I'm sure we all have, it hurts, and that's because all the nerves are on the outside of the cornea, okay? And so the original LASIK surgery used to actually machine the outside of the cornea, but that was very painful. So now they cut a flap and put it back. So there's only a couple of spots, and that's where the pain is. So it's a lot less painful. All right, so here it goes. I used to not be able to watch this video myself, but I've learned. And it's only the end that gets bad. So now you're going to see, Doc, they're holding it still. You have to be awake for the surgery. That's why I would never have it. And now the laser is going to come in, and you're going to see that it's going to raster scan. Because remember, you have to focus to a point. And so it's point by point by point. We're hammering that cornea. It's not on the outside edge, though. It's inside. And so here comes the part that's hard to watch. The surgeon is going to come, but I have to show you that a flap was cut. So here he's going to come. or she, don't have any idea who this is. Robot, who knows? Here he comes. I know it's gross, isn't it? But I have to show it to you, because you wouldn't trust me that the flap is there. It's gross. That's why I would never have it. There it is, and there it's cut. All right, so now we don't need to see the rest. The rest of this talk is just going to be a little bit about Nobel Week, because this is the favorite part. Most people tell me this is the favorite part of my talk. And I will say that, you know, we all watch the Oscars and the Grammys, but we don't watch this. In fact, we all watch in October who's going to win. But the big event is in December. I will also tell you, because I've been doing this thing about trust in science. You will see that, yes, he's there in this beautiful kimono, Dr. Hancho there. So at the entire week we were there were 6 to 8 Japanese reporters with their cameras on at all times. He was like a rock star in the center, and everywhere he went, those guys were around him, okay? 7 Americans out of the 10, and there was no American reporter, and there was certainly no Canadian reporter, okay? Anyway, they just think it's a bigger deal. So, but since you guys don't know, I'm going to show you. So we're all sitting in these red chairs. Only the present-day Nobel laureates sit there. The people sitting behind us are previous Nobel laureates. I got invited back, but when you know it was COVID, so I haven't gotten to go actually back. I have to come and show you these 2 people here, though. Because if I ever do get to go back, you want to remember that you're on, you know, people are taking your pictures all the time, and you really don't want to look like these 2 guys. They're really not happy that CPA won. Anyway, you will see that only Gérard and I are standing. Art Ashkin, unfortunately, was not only that he was 96, but he unfortunately found out he had cancer the same week he found out that he had won the Nobel Prize. So he could not come. His son came to get it for him. So he came first because it's alphabetical. So Ashkin won, but he had to sit around behind there. He was not allowed to sit in a red chair because he himself was not a Nobel laureate. But then you'll see it's Gérard and I, and that's because everybody in physics knows in the will, physics is first. So they are reading off why Gérard and I and Art got the Nobel Prize. Then after the event, you're given an invitation. You can see it's tucked in Gérard's arm. My husband is beside me, and he's holding his. Mine is probably behind my little clutch. We were each given 2 numbers. I was given the number 2 and the number 1. My husband was given the number 2 and the number 14. Gérard and his wife were obviously given the number 1, and then some other number, I don't know. I'll point out a few things. You'll see the beautiful red dress that Gérard's wife is wearing. Because this is a 4-hour TV show that is shown in Europe, every French woman, whether you actually win, and we know how few those are, or the spouses are dressed by a French designer. She is wearing Dior. And it was just lent to her for the day like it's the Oscars or the Grammys. And the jewels she's wearing were given to her to wear for the day by a French jeweler. I was asked who I was wearing. I went, no. I had to pay for that dress myself. Nobody gets free advertising out of me. So, so why are we there? And so then Francis Arnold, see, so physics is first, but Art's son could not be that. He's down number 10. And then comes chemistry. So we're saying, so what are we doing? We're in this room. Now, I have to say, the first time I gave the public talk after this, I said that we were in the gold room, because doesn't it look gold? This is the Stockholm City Hall, for goodness sakes. I know. I bet you even Ottawa, which is our capital, probably doesn't have as nice a city hall. And you do have the new one now, but no, it's not going to look like this. And I called this the gold room. And after the talk, my sister, who was in the audience, said, that isn't the gold room, Don. The gold room is where the dancing was going. I said, oh my gosh, there's a room that's more gold than this, okay? So what we're doing here, I'll come down this way now, is that you will see this, the 250 people at the head table are all standing there. And we're waiting. There's these people with these white hats. I was just back there at graduation time. This will all have some emblem. This is what you get when you graduate from a Swedish university, and the Swedish university emblem will be on the front of it, but they're all white hats. You know. Anyways, these people are working. They're all waiting for the royal family to come through these doors, and the royal family will then, and then we'll quickly get in a better line than this, and then we're all greeted by the royal family as they come down here. So then, oh, you see the numbers there. So what's the first? Is there number like 10 or 15 or something? So my husband will be 14. You don't see where I'm going because I'm going to number 1. So why do I go to number 1? I've already told you physics is first, but you have to follow the Royal Swedish protocol, and so you must sit boy, girl, boy, girl. So I got to walk in with the king. So now what would I say, having never met a king in my life? I will tell you what I'm saying here because I don't like to walk slow. And the person with the white hat was walking in front of us. Also notice that both the crown princess in her pink and gray and the queen, they always knew where the cameras were. I obviously never did. Anyway, we had to walk this slow. So I'm saying to him right there, I can tell, it's killing me to walk this slow. And he's saying, I say something every year, but who listens to me? He was an adorable man to have a dinner conversation with. And there we are. Now, let me tell you a little thing about this story. So the day before, on December 9th, you do have to, so December 10th is the anniversary of the death of Nobel, so that's when it's always on December 10th, regardless of what day of the week it is. So you sit down and you go through with your attaché, who was with you all week, to explain what's going on. But I had a woman, and she sat with me, and she told me all of the many rules, like I had to call him Your Majesty, but the lessers are known as Your Royal Highness, which to me, Your Royal Highness sounds better than Your Majesty. So I was very confusing. I had trouble with a lot of the stuff. But the one that I thought I can handle was, when the king stands, you stand. And when the king sits, you sit. I think I can follow that. So now you will see that we're already seated. And so that's when everybody starts to sit. But you'll also see most of the men look like they're helping whichever woman they walked in. When the king and I first get to our seats, the king holds my chair. And I looked back and I went, what the heck? I can't sit until you sit, but you don't seem to want to sit until I sit. Like I didn't know what to do. But I finally thought, well, he's king, so he must know, so I will sit. And so then he sat, and then we all got to sit. Doesn't it look like I'm explaining the photoelectric effect to him? I don't think I talk science to him at all, so I have no idea what I'm saying, but I have his attention. I love it. Okay, he was a lot of fun. And both of my kids were interviewed on TV. They missed the appetizer course because they had to be interviewed. And my daughter was asked if I would be liking sitting beside the king, and her answer was, oh, she's loving it. And I was. Okay, so the next day, your 14 guests go home, but you and your partner get invited to the palace to dine with the royal family. And this time, they line up, and you come in 2 by 2, and then the first 3 sort of back away and make that hole for you to stand there. Now, well, let me show you something. This came up in dinner earlier, but let me just point out something to you. Okay, so there's the, oh, I can't, you see the other woman in red there? Okay, so she's married to the prince. So you'll see our dresses are not identical, but quite a bit alike. Okay, so now the next time, I get all the way to the end, and what would I say to this very pretty woman who used to be a model before she became a princess? I said, I'm glad to see we're not wearing the same dress today. And she said, you and me both. Okay. I also want to say, though, tonight, Sir Frances Arnold walked in, who won chemistry when I won physics. She walked in with the king. My date that night was his son, who got to be the crown prince until he was 2, and then the Swedish parliament went, this is so wrong, and we're so into EDI, 40 years before the rest of the world. And so they said, no, it's the firstborn. So the older sister became the crown princess. Luckily, he was only 2, so he's maybe not too bitter. Anyway, he was my date that night. And I say, even when my husband's in the room, there is no movie or TV, Prince Charming, that can outdo this guy. Let me tell you. And with the king will talk to you for 20 minutes, and then he turns and he talks to the other person, and then everybody has to turn. So you all just do it. Whoever was sitting on the other side of him never got to talk to him. I had him the whole night. He was charming. All right. And that's where we were. And so it's amazing, isn't it? It's even golder. No. And I like to say somehow I went from just being a grad student trying to do a really good science project to landing in a fairy tale. That's what it felt like. I was just sitting there with my Prince Charming in this incredible place, dining on the venison that they'd killed. All right. Quite often, I show a different picture of Frances and I, but this is the picture Frances shows, so she probably prefers it. I will tell you what the one is that I show. The rehearsal at 10 in the morning. The men are all standing like this, waiting for their cue to go in. And she and I are laughing our heads off because we were there to have a good time the whole time. But anyway, it looks like we're holding up our actual medals, but we're not. That's just the gold-wrapped chocolate coins. I will also tell you that in my daughter's gown, I've never known this, but she had huge pockets. Like she had a big full skirt with huge pockets. And so only on our table were there a lot of these chocolate coins. The other tables where she was, everybody got one coin. My two kids, who were in their 20s, so they're not young kids, actually waited until everybody else was gone, and they went right down the center table, and my daughter came home with 50 of those in her pocket. She took them to her group meeting, and her advisor said, take this. We got Nobel Prizes at our group meeting. All right, so this is Frances Arnold. We did make history. It was the first time in the history of the Nobel Prize that two women won in the physical sciences at the same time. She won in chemistry when I won in physics. And since then, of course, we've had two women in chemistry together. And we've had two more women, but not together. All right, so here's the most surreal moment of the week. This is when, like, as soon as you get your medal and everything from the king's hand, they take it away because you don't want to go to the ball holding on to that. And so that's it there. You'll see that we all get our piece of art. It's a different picture. I'm not showing the picture that shows the art, but we each get our own unique piece of art. So it was the same artist who did all three of the physics ones, but each one is different. It goes, the other side is the certificate, and then the gold medal's in the red box. Anyways, then they give you this pen, and they ask you, but before you sign the book that you'll see me signing, for all the physicists, they open up the book to show you Albert Einstein's signature. For me, they showed me Marie Curie's and then Maria Goeppert-Mayer's. You do get to look through the whole book. Then they ask you to sign. And it really was the most surreal moment, thinking, how am I signing the same book as those legends of our field? So I think I'm going to end there. I am. Thank you very much. You want me to stay up here?
And very inspirational, going from the most fundamental physics that all the students are going, yes, we're seeing it again tonight, to this amazing ceremony. So thank you very much. We have time for questions, and we have a microphone, so I'd invite anyone with a question to raise their hand, and Rima will bring you the microphone. Okay, well, while people are thinking their question, I'll ask, what did your grad students think?
Actually, you know, I felt bad because I had just had a student finish with their master's, and we were supposed to all go out for lunch that Tuesday. And then my colleague, Joe Sanderson, showed up with my grad students to my house. And I said, I can't, it was such a crazy day. First of all, I was having my ensuite bathroom redone. And so plumbers were there. They had turned off the water. I had my neighbor showed up with flowers by 7:30. I had a photographer. I had a reporter. It was just crazy, crazy, crazy. It's right from the get-go, right? And so we had to postpone that, but they said it was okay. So they were excited. The dean came in and cleaned my lab so that when the reporters came in, it didn't look like the mess it was.
Sounds very realistic.
So do you want to come in here? It's easy, or I'll pass it on to you. Sorry.
Yes, hi. I once did research in femtosecond laser myself. So I just wanted to ask you humbly, what applications do you see now that the technology is advancing and laser techniques could also improve and only get better? What is the range of applications you see to help the world today?
Help the world. I never tried to help the world, but I myself am still working on short pulse lasers, although not CPA, but still intense. And I am trying to make out into the mid-infrared, and so those mid-infrared pulses could be used for sensors for the environment. We're also still trying to make really, really short pulses so that we can make molecular movies of how the energy goes through molecules. And the last one, I'm working with the inventor of laser wake field acceleration to see if we can just accelerate up to KeV to take away the tumor after surgeon has gone most of the way through, but let them keep the last little bit there, and we'll just use KeV electrons maybe to eradicate that. And we're hoping to accelerate at the end of the fiber. But there's a few things that have to be developed to make that happen.
I'm really curious. Was the food any good?
Yes, you know, the king is, what do you call, an epicure, is that what it's called? Like, he really loves his food, and actually he's the one who kills the venison that is given to us at the palace every year. Well, I don't know about him, his hunting party may not have actually been killed by him, but he goes out hunting. But no, he really likes the food, and no, it is really excellent, excellent food with the 5 kinds of drinks. But you're also not allowed to get up from the table at all, right? So you want to be careful how much you drink because you can't get up. And so although it was their parliament was having crisis, and so even the king was saying, I'm surprised all of our ministers are sitting at the table tonight, and some of them did have to get up and go. But you're not supposed to. And so there's the 5 drinks. I mean, the Swedes really know how to party. Now, it was not at these formal ones, we did not have it, but then I had to take gowns for a number of parties. And along with the 5 drinks that seems to sit there, there's a different drinking song that goes with everyone. And so you have to sing the song that goes with the drink and then drink the drink and on you go. So they do know how to party in Sweden. But the food was excellent, yep.
Are you still doing any researches?
Yeah, I should be. I do spend most of my time. I am a 100K flyer. I do mostly, and this is my 3rd talk, and apparently I'm giving another one tomorrow, so 4 talks in a week. So I'm mostly just going and giving talks, and my students are flailing, and they're finally been with me long enough, and they've made all the mistakes now, so hopefully we're all learning together how to use these new lasers and push slowly along.
After accomplishing something so significant, what would you say serves as like your motivation to keep, I guess, pursuing whatever breakthroughs you're still, looking into?
You see, I got asked at the very first press conference at the University of Waterloo, did I want to save the world, which is sort of what this other question was, and I never did. And so I didn't need to, and I didn't think about what I did as being big and incredible. It was, to me, we had a lot of fun. Gérard's whole group had a lot of fun, and we helped each other with our projects. I still like tweaking lasers. I still think it's a fun thing. I still get a thrill out of showing high school kids how red turns into green light and all this other stuff, or white light generation where the color turns into all the colors of the rainbow. It's cool. And for 10 years we thought it was magic. Scientists did not know why it worked, but we used it. And I helped figure that out as part of my postdoc. But I still think lasers are just a fun thing to play with, and so I still consider it playing. I'm not out there trying to save the world.
Hi, I'm just wondering, oops.
Where are we?
Over here.
Okay, thank you.
I'm just wondering if achieving what you've achieved, do you still feel imposter syndrome at times?
All the time. And I've talked to other Nobel laureates. I mean, and it was a male Nobel laureate that said it's like imposter syndrome on steroids. Because once you win, everybody thinks, oh my goodness, you're so smart. You know everything. And I've been on a panel with Sylvia Earle, who's one of the amazing women that first went into the oceans to study, down and lived. You probably don't know this, but before the Apollo missions went to the moon, they had 15 women go into a submarine and stay a month way under the ocean, further than anybody had ever gone. She was one of those people. And this is back in 1950s, an amazing woman. And so I'm sitting on a panel with her about oceans, like I know something about oceans. It was like, I don't know why am I sitting here on oceans. But then I was sitting with Apollo astronauts talking about going to Mars. Well, what the heck do I know about going to Mars? But who's going to turn down a chance to sit with Apollo astronauts? I mean, so you do it, but you think, okay, you're going to have to figure out something to ask me because I know nothing about going to Mars. And so, yes, you're always being asked for things that you don't have the answer for, And then what's the other one when I talk about going up to 10 to the 29? Dark energy. What's the particle that's going to be dark energy that people are looking for? Who's my high energy physics person here? Anyway, gluons or something, right? Is that what? Could be WIMPs. Yeah, and they're going, can you use lasers to find that? I went, how do I know? I don't know. Maybe, but it's above my pay grade. So no, I mean, I've never really felt it as much as since winning, and I've talked to some of the men who've won, and it may even be the first time for them, but probably not. I mean, I think women think it's much more a woman's thing, but I've met very few people that haven't suffered from imposter syndrome. So.
Hi. We use nanosecond laser and femtosecond laser running the laser ablation, ICPM's experiment, analysis of minerals in geoscience. Mm-hmm. We observed a lot of energy.
With LIBS. You're talking about LIBS.
LIBS.
Yep.
Thermal effect. when we use nanosecond laser. So my question, but for femtosecond laser,
You do
we
not,
did not.
of course.
So I'd like to know what really the difference in terms of laser and matter interact.
Okay, this is because the libs, which is so you know, it's an intensity effect that blows off whatever particle, and then they studied the blow off of the solids that are coming off. But it's an intensity effect, which is energy per unit time, right? The same thing as a nonlinear effect, it's energy per unit time. And so when you use a really short pulse, you're not using very much energy. You have the same intensity for a whole lot less energy. But heat is how much energy is getting converted. So in the case of the nanosecond pulse, you're depositing 1,000 times, or actually it's 1,000,000 times, if you're, it depends if you're doing femtoseconds or picoseconds, but a picosecond to a nanosecond for the same intensity is 1,000 times more energy, and that's why it's going to heat up a lot more.
Okay, we'll just have the last question here.
Yeah, I was just wondering.
Thank you for asking me a question that I do know. Okay, go ahead.
I was just wondering if there's an idea in physics, in your research, or just in general, that you find particularly beautiful.
Oh, particularly beautiful.
Yeah.
Well, you see, my favorite, and this is what I wanted, someone was asking me about my physics education research. I really wanted to show undergrads, and I do show high school students when they come into my lab, white light generation. Because I've already mentioned it, right? And when I told my son about this, he said, what's the big deal? A prism does that all the time. I went, no, a prism takes white light and turns it in, breaks into the colors. Whereas with our short, intense pulses, you can just take any clear object. So I usually take the students out and fill up just from the water fountain a cell of water, right? And just show it's just ordinary water. But then we can also have clear plastic or clear glass. And then we take our infrared pulse and we show off the gradient that there's only infrared light there. You can't see it with your eye, and it goes off the gradient at a certain spot. And then you put it into this clear object. Every color comes out from the infrared to the ultraviolet, and we throw it off a gradient and show all the colors are created. And it's an absolutely beautiful thing to see, and I love watching it. Now, I have to say, because I'm also doing this other thing called multi-frequency Raman generation in my lab as an actual scientific thing, because I did my postdoc on white light generation. And it's a picket fence of colors. But again, they go all the way from the infrared to the ultraviolet. And then, thinking about my talk and wearing laser goggles and stuff, the fact, actually, and I keep saying how efficient it is, and I make sure we have the IR goggles on, but actually all those colors could probably blind us too, and we don't wear the goggles for all those colors. So when I get it set up again, we're going to have to be more careful. But on the other hand, it's such a beautiful thing to see. It'd be a shame to have, well, actually, you couldn't, because it's every color of the rainbow, so it would have to be black. So how could we see it? So we'll have to figure that one out. But I will make sure my students are safe. But again, I find both multi-frequency Raman generation and the white light generation, I just think it's like magic when it comes out. Yeah. And this is why I say to a lot of my students, the physicists are really just explaining the magic. Okay.
What an amazing presentation, a masterclass in science communication. Thank you so much, Dr. Strickland, for sharing your passion for your science and your humor and just being so generous with your time. Let's thank this amazing speaker one more time. So just a small token from us at Carleton.
Thank you.
We would love for you to sign the poster so that we can share it. Oh, it's going to fall. There we go. So if you can sign that for us.
All righty. Where do you want me to
So I just want to take a moment to mention that Dr. Strickland will be back on our campus tomorrow morning, 9:30 a.m., just in case you forgot, Ridgecraft Hall, for a more specialized colloquium from nonlinear optics to high-intensity laser physics. Stay up to date on all things happening at Carleton Science using carleton.ca/science or at Carleton Science tag. Thank you so much for sharing in this really special night, everyone. Have a great night.
I'm going to grab my thing again.
Yes. Absolutely. Let's get a quick picture. That's right. Here, yeah. Oh, that was so amazing. Yeah, oh, and it's taken from way back there.